Okay, guys, let's get started. Happy Monday. Monday is good day. So let's see what we're gonna talk today. Last week, we finished combinational logic circuits. We said combinational logic circuits are very simple kind of circuits that you can have this class. You just have input and output. They are acting like a box. You get some input. Right away, they make decision and make output. And today, we're going to go one step forward. We want to see if we can store or state and make decision, not just based on input, but considering previous history of the system. So the history is very important to make decision in this case. And it's very similar to how we make decision. When we want to make decision, we're not going to make decision just with what we see, but from what we learned before. That history can make better decision, of course. So that's what we want to talk today. We're going to talk about sequential logics and different type of sequential logics, synchronous and asynchronous logics. When we have clock, when all memory parts are synchronized with the clock, with a global time, or there is no clock, they just make decisions by themselves. And see pros and cons of those systems. First, let us start with definition of sequential systems. So in digital logic, we have two main type of circuits. We have combinational that we had before and sequential. In sequential logics, we have memory. Why we need memory? To save our state. What is a state? State, really. Any idea? What is the state of a system? Huh?
Like what's in your memory?
What is the memory? Or in definition, we can say whatever can summarize the system in this moment called state. The minimum values. The minimum values that can summarize the system in this moment called the state of the system in this moment. Like, for example, in elevator, what is the system? What is the state of the elevator is where it is. For example, is in the floor 2, and where is going, for example. These two values is enough, maybe, or maybe more. Maybe somebody else entered another input, go somewhere else. That's also considered another input as well. So these values summarize the system, but they need to be minimum. We can put lots of other information, but we don't use them. So a state of the system is a minimum number of values can summarize the system. That's important. And these values can be stored in the memory. Why? To use them for the later. To use them for next decision making. Okay, that's a sequential sequence. So the sequential circuits are those when the output depends on not only the current input, but also from the history of past. And we can remember that. We can use memory to store that. We're going to see in these following classes how we can design memory. We call them storage units. How we can design a storage like registers. How we can do that. We can see how make latches or flip-flop. We're going to see those maybe next class. Mathematically, what we want to do, we want to make the output not just like in combinational logic, the output was just a function of input. But in sequential, we want to find the output that this is not just based off the current input, but also based off actually previous state. This is what we want to find. And this function is still Boolean function, but this function has some elements coming from before. Like imagine you design a circuit like that. Just example. A, B, C, D, for example. And these outputs, this is normal combinational logic. But imagine we have a loop that from the output coming to input. It's like that. So the output, if, for example, we store that in a memory or even not, we just make a loop from output to input, it means we are using the previous decision. We are using the previous output to make new decision. However, this system is not going to work because it's going to make lots of, we know if we don't use time to synchronize sequential logic parts, it's going to make a problem because of propagation time in gates are different. So for example, here you wait for this to input, but maybe this input coming later than this input. And this going to make some problems that we call them hazard. We're going to see them maybe next class or today. Hazard happening when you don't have global clock to synchronize all parts. And you have input from previous states. So in this case, we're going to have problems. Okay, let's see them. Let's see what we can design them. But any question in this part? Okay, I'm going to explain that much more. Don't worry if you didn't get the point. But mathematically, the function, the Boolean function is getting current input and previous state. And a state is those values that summarize the system, the minimum values, of course. And we need memory for that. Why we need memory? To have previous state. And the memory needs some ordering or timing, because you are considering wants to use previous state, and when it gets ready, you want to make action, you need some timing. And this timing needs another part for the system that is called clock. And clock is like, it's not like our clock, it's very precise clock. So the clock is just a pulse that has some characteristic, for example, some edges, rising edges, for example. These rising edges is important. We also have clock white that showing what is the actually frequency of the clock, but we not consider that right now. But this part is important. The rising the clock is the time that circuit makes decision in that certain time. So sequential system need to be synchronized with this time. We're going to see that soon. And how they work. So if input change, the circuit process that change, and based off this current state and new input, we make the new states. This is how it works. And the system is need to be synchronized, at least the part that is storing states need to be synchronized with the signal that called clock, that we're going to see that soon. So that's a sequential circuit. This is what we want to talk today. We have so many applications for that, like, for example, elevator that I explained is one of them. Or vending machine, when you go and pay money to get, for example, a water bottle or can of Coke, for example, when you enter your money, it starts collecting and summing and adding the coins that you send. When it gets, for example, certain amount of money, like $1, it releases the water. Imagine that's a coin one. And here, for example, in this system, this is considering actually filling the bottle. Like imagine you have, I don't know if I can find a space to draw it. Like, for example, you are designing like a manufacturing, and there is some bottles that coming, like, for example, they are like wine couple bottles. And they are here, there is a part to fill them up. My painting is so bad. Okay, maybe it's here. So here is what is putting inside and going after filling. Okay, so imagine this is a pipeline. The bottles coming inside, filling with the wine or water, whatever, and when it's done, it's finishing. So a state is starting here. We need some timing for filling. It's not right away. So for example, it needs 25, I don't know, second, for example. So it's coming here. The system is like a state machine. We call that state machine. We're going to see and explain that later, but I just want to say how it works. So in a state 0 is here. That is considering if the bottle is not in exact place, wait. As you can see, it's wait. Waiting means the state back to the state of wait. If yes, a state filling. Open the, for example, the water, and water going to start, and it takes 25, for example, second or millisecond, whatever. And when it's done, it's pass it to the next stage and coming back for the next, and stay waiting to see if it's ready, start opening the water. And this is the system that we can see in so many manufacturing, and they are all need some previous state. And where is the previous state? This number. This state starts from a state 0. The state 0 is in this spot to wait for opening the water or wine, for example, or whatever. This is 0 that counting to 25, and then pass it to the next step. So that example is for bottle, filling the bottle example. Any question about this? Okay, let's see what type of sequential circuits we have. We have normally two main categories for sequential circuits: more and melee. More is when actually we have a combinational logic, some elements of memory, and we use this memory to make next decision, and the output going out from the memory. This combinational logic, most of the sequential logic also have the combinational logic, because combinational logic is just and or that makes these connections between this state. We need those all the time. So in more machine or more circuits, output depends only on the current state. We might have some input at the beginning, but the decision happening in this loop, decision happening between, so the output is just a function of actually a state. And this state is the memory. So this is how more machine working. So the output change after transition in a state. When a state changing, and when transition happens, anybody can help me in this case? When the transition happening, when the clock edge rise edge comes. So the clock is the timing part. So they are, all the memories are connected to the clock. This is the clock. And which part of the clock? Rising edge. So when that edge coming, the decision happening and a transition happening. So the transition is synchronized with the clock rising most of the time. Most of the system working with the rising edge of the clock, some of them with the falling, but you just consider it, at least in this class, with rising the clock. So this kind of circuits that are synchronized and actually they are just using previous state to make output, they look simpler and more stable. But a slightly slower response. So let's have the cleaner version of this picture here. This is the Moore machine. Like one of the examples that we can see is like the system that controlling the door, controlling the system, automatic door controller. Example of that. So in automatic door controller, like for example, you have a door here, and this door get open automatically when, for example, the user coming to pass get open, and then it's passing get closed. So you can design that system using a more system. This is the wall here, for example, and this is the door. So this door controller needs a circuit to make decision based off the previous state. Considering the user is coming is just for the first part. After that, making decision is mostly based off the previous state. Previous state is the door open or closed. That's the state. So you make decision if the state is closed, stay closed or get open. You get the point? If the state of the system is already closed, you want to stay closed. or get open. So this system is more because the output is just related to the current state. That's an example of more. Let's go for another type of system. We have another type of system is melee, more advanced, or melee, sorry. So melee, as you can guess from the name, it gets some food from somewhere else, gets some other input. So melee get another input. It's not just a state, make decisions. So the function, the output is not just based off the memory, but from the input. Input and a state. A state is in the memory. So the diagram, let's up. Maybe I cleaned all of it. Yes. So as you can see, we have some combinational logic, the input coming to the combinational logic, and we have some state, we have some memory to save a state, and then using that state to make decision in this combinational logic and make output. This is two the general, yes.
Why does the output not come from the combinational logic?
It can actually, yeah, of course, it can go from there too. But normally, that's why they are two general case of actually sequential systems. Yes, we have some systems that you can get output from the combinational. Yes, that's correct. But most of the time, if we just want the state is in memory. That's why we just take it from memory. Here also we can take it from here. Yeah, your question is actually a good question because because in the book that I'm teaching is mentioned from here. This always was my question. Why we don't take it from here and there we take it? But I think we can take from memory or there. It depends what we want to take out. If we want to take out the state, we can take it from the memory here. But still we have the input to make decision and this combinational logic. So maybe here we want to involve input, kind of. That's why we take output from combinational logic. But it depends the system. Anyway, in a system that input involved to make decision, that system called melee. I think you can get it from memory or combinational. Doesn't matter. That's not actually that's important for decide the system is more for a melee. So this output doesn't matter coming from here or here. And here also the same. Output can go from here. But good question. Any more questions? So that's so a melee consider faster and use fewer states because maybe you don't need to save lots of information for the state, but it's more complex because you're considering input. However, more application of this kind of system more. You most of the time need to get, if you want to have better decision, you need to have some observations from the environment. For example, for the heat system of measuring the controlling the heater for the system, like furnace, is working like that. You have some sensor to read the temperature of the environment, and based off the previous and the information that user asked, for example, user asked, okay, put temperature in 70 Fahrenheit degrees. So based on this information and sensors that consider input, make decision that what is the decision? Do I need to turn heater on or off? So this is how these systems work. So as you can see, lots of applications. Lots of applications. So, or another application can be vending machine that you see everywhere. Like in vending machine, however, the vending machine that using just with coin, using coin, coin operated. In this vending machine, imagine you are entering coin little by little, and when it gets enough to a certain value, for example, $1, it's actually release the drink. So the release drink immediately after reaching that certain value. So that kind of system always get input. So the input is the coin that you are entering. So this kind of system considered a melee machine because making decision is based off previous values that you had, like for example, add up like 90 cents, and you need another 10 cents to become $1 to release actually the. So in this case, output depends on both state, current credit, and input. What is input? The coin, new coin. Coin that enter. So this system considered milli. Any question? Okay, let's see how we can deal with clock. Oh, okay. Here is just mentioned that the output is function of state, Boolean function, or state entity. We have two types of sequential logics, synchronous and asynchronous. So as I explained at the beginning of the class, the synchronous has clock. So normally, synchronous change the state sync with the clock signal. So if I want to write a summary of how it's acting, I can say change of state occur in sync with clock. And like, for example, counter. Imagine you have a counter that counts between 0 to 9, for example. And this counter has a clock. And the clock is like that. And you want to make, for example, 0, 4-digit counter. 0, and then 1, and then 2, and 3, and 4, and rest, and so on. And this counter is actually based off the previous state. Is already inside, has some memory to save the state. And when the clock coming, change the state, add it up, and make output. So this system is a synchronous system because it has clock. This clock is the global clock. If you have multiple memory in this counter, they all need to set with this clock at the same time. They make decision all synchronized with the clock. Which part of the clock? The edge of rising edge. So this type of systems are considered synchronous system. But we also have maybe some issues about that. Anybody can guess what is the issue of synchronous?
Trying to adjust the state address at the same time. Take over the other and then shove the back.
So that's a good part. So in synchronous, that's not going to happen because they are all synchronous with the one time. Yeah, so that's happened when you don't have a time. What's your point?
So we were talking about how you're basing everything on a clock. That means if you want to do multiple things at the same time, you have to wait for the next clock cycle.
Yes, makes it slower. Yes, you need to wait for the clock. That's a good point. You need to wait. So it means, and the clock make the system slow because clock need to be synchronized with the longest path. Am I right? So you need to make decision based off the longest path in the system. Some decisions happening in your system very fast, but you need to see which decisions need more time, and we put the clock based off those, delayed time. So that's why the synchronous systems are normally slower, but more stable because we are designing the system based off the clock. The problem like hazard not going to happen if you design it right. Okay, we're going to see that later as well. So that I clean this up. So that's the clock that we talked about. And rising edge is an important part. Making decision is based off this edge. And in asynchronous, we don't have this clock. So the behavior of the system defined from the knowledge of input. Like before, like combinational logics. Whatever we become as an input, we make decision right away. We are not waiting to synchronizing. We are not synchronizing with anything. So sometimes problem happening in this, but it's so fast. Why is so fast? Because you just make decision when the input coming. The only delay is the propagation delay between gates. And that's very, very low. So it's very fast, but the system is not that stable. We can see how we can fix it, but it still is very complicated. That's an open subject if you want to go for a master's or PhD. Designing circuits and asynchronous circuits are a very open concept. Still so many people working on that. But let's talk more about synchronous systems. So as I said, in synchronous design, they are all sync with a global clock. When I'm talking about global clock, means if you have multiple memory, for example, in your system, or any parts that is storing a state, they need to be synchronized. They need to be all connected to the same clock. And these memories, most of the time, flip-flop and registers need to connect with the clock, as I mentioned. And it's easier to design because you don't need to worry about problems that are happening in gate propagation. And you can easily simulate it because whatever you are thinking is going to happen. But in asynchronous design, maybe you write something in paper, but in reality, it's not working like that. Imagine you want to design a circuit to just do XOR. But this XOR, XOR make decision based off the not equality. Like imagine here is A, and B, and if it's A not equal to B, open the door, for example, become 1. So this is a very good example. Look at what's happening. Imagine here you store 0 and 0. So if it's 0 and 0, what is the output? The output, because these two are equal, is 0. That's 0. The output is 0. But suddenly you want to make these two register. For example, these two are the only difference here is that they put these two values in a memory. That's a memory. That's a register, for example. Register is a type of memory that you can use in computers. So in these registers, suddenly you want to change it with 1, both of them at the same time. You suddenly change them to the 1, but imagine because of those memories, there is no clock here. One of them, because this register has multiple gates inside, and those gates are not exactly have the same propagation timing. Because this is hardware, it's not something it's just passing electrons between layers. It's not something that you can make decide. In practice, it's not working like that. Like suddenly it was 0, you have a 1, 1, and then 0. This is the result of this propagation timing. Why this is happening? Because these registers A and B, when you are at the same time change them from 0 to 1, they make output not exactly the same time. Some of them has more propagation time. So they make 1 suddenly, and this 1 is called actually hazard. And this is something that or glitch, is also called glitch. Like a spike or hazard. So this spike is happening in practice, in the lab. But in paper, that's okay. That's the formula is exactly correct. Like you say, F is A bar B plus A B bar. That's the formula for that. Like math saying that's fine, but in reality, you see this. So, oh, what? This happened? The math say this because of this problem. This is something that you can see in practice. So in simulation, synchronous systems working fine because exactly they are based off, if you put the clock here, if you have clock, this is not going to happen. Okay, let's clean this up. Any question about this? So for processors, for controllers, for sequential circuits, this is using a lot. Synchronous systems use a lot. Most of the systems that we're going to learn in this class are synchronous because it's simpler. But if for higher degrees, if you go for master's or PhD, you might encounter with asynchronous design as well. So for example, counters, shift registers, they are all need be sync with the clock. So features, timing, controlled by clock, speed is slower, complexity is lower because it's easier to design. Example like counter, for example. But as asynchronous design is no clock. You don't have a global clock. So circuit responds immediately to the input change. When the input change, system changing output immediately. because there is no waiting. There is no synchronizing. Just make decision based off input. But this input sometimes not making proper answer, but it's so fast. The timing is so fast, but it's going to make some problems that we call them race condition. In that example, we have race condition. Race condition means the condition that one of the inputs get ready faster than the other, and make glitch or hazard or problem. That problem is called race condition. We're going to see that. And require careful design to avoid glitch. That's something that we need to take care. So in kind of systems that we don't need clock, like a handshake system, handshake-based system, like networking. In networking, you don't have clock. You do handshaking. You do, okay, a request and response. You send message, oh, can I, like when you are talking with a walkie-talkie, you say, can I talk? And that's going to let you answer. That's why you don't need clock in that case. So this is, we call it handshaking. Handshaking is a kind of system when, you know, two systems, instead of synchronizing with clock, synchronizing with the request and response, you know, or request and acknowledgement. So that's called handshaking. And for systems that need to have a lower power design, like the battery, when you are not using your system, if you have clock refreshing memory every, for example, millisecond, anytime the edge coming. But you don't want to this wasting energy, because refreshing needs lots of wasting. If you don't use it, it wastes energy. So for low power design, you can use this synchronous logics. In this case, for example, when you are not using the memory, memory doesn't need power. It's get off. And when it start working, it start on. So that's the type of system that doesn't need to be synchronized by time. Synchronized by acknowledgements. You have request and acknowledgement. So, okay, I want to use memory, so memory get on. Like when you click in your keyboard, it start working. When you are not using that, it's not synchronizing with the clock. It's not wasting energy. So this type of systems called asynchronous systems. The timing is not controlled by drive. It's like event-driven, based off the event. And here I compared these two in this table. Speed is faster, and complexity is very complex. And example, for example, ripple counter or ripple effect that you had in multi-bit adder, it was the same problem. We call it ripple effect. So this is asynchronous digital logics. So the problem that we have here is also called race condition. I'm just going to explain this here. That's the last slide. So the race condition is a condition when you have different input with different propagation time. And if this propagation time is not same, the output change in a very little timing that makes problem for the system. So example, I had one example there. There is another example here. Imagine we have two input A and B, and this A and B are in a register, and you AND them together. Here, just use one AND, and this A and B. if, for example, here is 1 and 1, the result is 1. 1. The result is 1 because they are 1 and 1. But as suddenly you want to change this state to 0 and 0. You want to change this to 0 and this to 0 at the same time. But when you do this changing, because of delaying time between these gates in these two elements of memory, at one very little second, here is 1, this is stay 1 and this is 0. So this 1 becomes 0 very little time. That little time that going gets 0. Why? Because this is still is in transition time because they are not synchronized. And this problem happening. And this is something that we call it glitch. And is like a spike that happening or hazard that because of this and this condition called race condition. Why is race? Because depends which one doing that first. Yes.
How in industry would you avoid this problem? Like, because realistically, I don't, or personally, each right now is in here. So how would we avoid this problem?
It's I don't know if you want to say because it's an open project. It depends that kind of project is not a solution that works for everything.
There's some general.
It might be, but I don't know. But it might be, but I can check and if there is a general way. But one way to do that, I already mentioned 2 methods to solve it. I think I have it here too. Using like handshaking is one of them. Handshaking is one of them, or actually kind of instead of using clock, we find another way to synchronize. This is how the general work is like that. Find another way. Instead of using clock, you use another thing, like acknowledgements. Send request and acknowledgement. That's one of the general way. But based off the system, you might have different methods. But I will check to see if there is a more general way. Okay, any other questions? Don't forget to take a look at this AI agent. They are talking about this subject very nicely. Have a good day.